The trail is quiet in the way only the Amazon can be quiet. Not empty, but layered. Leaf litter holds the heat of the day like a memory. Moisture hangs low, clinging to bark, to moss, to the skin of anything that passes through. In the soft half-light beneath the canopy, movement is subtle. A twitch of fern fronds, a ripple of ants crossing a root, the slow, deliberate hop of a squat brown shape crossing the path. At first glance, it looks harmless. A toad, thick-bodied and unhurried, pauses in the open as if it belongs there, because it does. Its skin is rough, earth-colored, perfectly tuned to the mud and leaf rot beneath it. No warning colors, no threat displays. Just an animal going about its night. The camera draws closer, and that illusion begins to fracture. Along the parotoid glands behind the eyes, tiny beads of milky fluid swell and glisten under the humidity, collecting like dew that does not belong. This is not sweat. It is not slime. It is chemistry, a defensive secretion pressurized just beneath the skin, ready to flow with the slightest provocation. The toad does not need to bite, sting, or chase. Its weapon is passive, patient, and devastatingly effective. This is the marine toad's strategy. Let the world come to you, and let chemistry do the rest. Bufotoxins are not a single poison, but a complex chemical cocktail, refined by millions of years of evolutionary pressure. Cardiac glycosides, biogenic amines, steroid compounds, substances that interfere directly with nerve transmission, heart rhythm, and muscle control. For predators, the message is immediate and brutal. One bite, one lick, one wrong decision, and the body begins to betray itself. The heart stutters, saliva floods the mouth, muscles tremble, seize, or collapse into weakness. In ecosystems where almost everything eats something else, the marine toad survives by being an awful mistake to make. Birds learn it, mammals learn it, reptiles learn it or die. The toad doesn't chase danger away. It trains the forest through consequence. What makes this chemical shield especially dangerous is how easily it crosses boundaries. Unlike venom that must be injected, bufotoxins work through contact. Wet skin absorbs them. Mucous membranes pull them in fast. Eyes, mouths, noses. Soft tissue turns a defensive secretion into a direct internal assault. In the Amazon, where humidity keeps hands damp and sweat never truly dries, exposure doesn't require recklessness. It requires routine, a hand that brushes a toad while stepping off the trail, fingers that wipe sweat from a brow, a dog's nose that investigates movement in the dark. The chain is short, fast, and common. The camera follows that chain, not as a reenactment, but as an observation of how environments create risk without intention. A hiker pauses to adjust a boot. The toad freezes, trusting stillness more than flight. Skin touches skin. Nothing happens immediately, and that delay is part of the danger. The toxin does not burn. It does not sting. It waits. Minutes later, irritation creeps in. A tingling in the lips. A metallic taste, a sudden awareness that something is wrong. Panic follows not because of pain, but because the body begins to misfire without explanation. The heart feels too fast, then too slow. Breathing becomes conscious instead of automatic. The nervous system, hijacked by compounds evolved to stop predators, starts sending mixed signals. Dogs are even more vulnerable, and the forest knows this. Canids investigate with their mouths. They lick, they bite. A marine toad encountered at night becomes an instant emergency. Frothing at the mouth, disorientation, seizures, not because the animal attacked, but because it existed. In regions where these toads are common, locals recognize the signs immediately. They flush mouths with water, keep animals calm, seek treatment fast. Speed matters because the danger is not tissue damage. It is physiological chaos. The toxin does not tear flesh, it scrambles systems. This is where fear enters the story, and it is a different kind of fear than fangs or claws inspire. There is no wound to point at, no blood to explain what is happening. The threat is invisible, internal, and accelerating. Evolutionarily, this is a powerful defense. Predators that survive the encounter don't just learn to avoid the toad, they remember the sensation of losing control over their own bodies. The forest runs on memory as much as instinct. The marine toad's role in the ecosystem extends beyond self-defense. Its toxins shape predator behavior, influence feeding routes, and even affect population dynamics. Animals that can tolerate low doses gain access to a food source others avoid. Some snakes and birds develop partial resistance, a biochemical arms race playing out molecule by molecule. In areas where marine toads have expanded beyond their native range, this balance breaks. Predators without evolutionary exposure die in large numbers, not because they are weak, but because their bodies have never encountered this chemistry before. The toxin does not discriminate between native and invasive. It simply does what it was built to do. Thermoregulation ties quietly into this story. The toad's activity peaks in warm, humid conditions that also increase toxin fluidity and skin permeability. Heat keeps the chemistry mobile. Moisture keeps it transferable. The same environmental conditions that make the Amazon feel alive also make this defense more effective. Nothing about this is accidental. Evolution rarely is. The toad's rough skin slows water loss. Its nocturnal habits reduce predation pressure. Its chemical arsenal fills the remaining gaps. Survival here is not about dominance. It is about being the wrong choice. As the night deepens, the trail fills with movement. Insects rise from the leaf litter. Frogs call from hidden pools. Somewhere nearby, a predator pauses, reassessing a hunt that will not happen. The marine toad resumes its slow crossing, unbothered by the attention it does not notice. It does not need to advertise its danger loudly. Subtlety works better. The forest learns quickly. The final image lingers on the toad disappearing into shadow, toxin beads drying back into the skin, threat withdrawn, but never gone. This is the quiet truth of the Amazon. Danger does not always announce itself with teeth or violence. Sometimes it waits patiently at ankle height, wrapped in mud-colored skin, letting curiosity and routine do the work. The forest does not need fangs to poison you. It only needs chemistry, timing, and a body evolved to turn contact into consequence. Under bark and stones is where the Amazon hides its truth. The surface looks calm. Fallen logs softened by rot, slabs of peeling wood pressed flat against the soil, stones darkened by moisture and age. These are the places hands go first. A hiker steadies themselves on a log. A camper clears ground for sleep. A worker flips debris to make a path. In daylight, these gestures feel harmless, even intimate. Human skin touching forest skin. But beneath that thin layer, in the compressed darkness where heat and humidity never quite leave, something is already coiled, already awake. The camera slides under a lifted slab of bark, and the world compresses. Space narrows, light fractures into thin blades. The air is warm and stale, heavy with fungal breath and the slow metabolism of decay. Then the movement resolves. dozens of articulated segments flowing as one, a body that does not slither or crawl so much as surge. A scolopendra centipede fills the frame, its length exaggerated by the confined space, its legs rippling in perfect asynchronous rhythm. This is not an insect that waits to be discovered. It expects intrusion, and it is built to answer it. Scolopendra are apex invertebrate predators of the leaf litter, and everything about their design reflects that role. Flattened bodies allow them to slide into impossibly narrow gaps. Dozens of legs distribute force across uneven ground, giving them traction on bark, soil, stone, even vertical surfaces. Antennae sweep constantly, reading chemical traces, vibrations, air movement, a sensory net tuned for darkness. They do not rely on sight. They do not need warning colors. In the underworld of the forest floor, speed and certainty matter more than display. Venom delivery is where this animal crosses from impressive to unforgiving. The first pair of legs has been transformed into forcipules, curved, hollow, claw-like appendages hinged beneath the head. They are not jaws, but they function like them, snapping inward with force driven by powerful muscles anchored deep in the cephalic segments. When a centipede strikes, it does not nip, it clamps. The forcipules pierce skin and inject venom directly into tissue, often on both sides at once. The mechanics are efficient, brutal, and optimized for prey that struggles violently. The venom itself is a complex blend of neurotoxic and cytolytic components, designed to overwhelm quickly. Sodium and potassium channels in nerve membranes are disrupted, sending chaotic signals through pain fibers. This is why the sensation is so often described as electrical, not sharp like a sting, not dull like a bruise, but deep, radiating, and alive. Pain spreads outward from the bite site in waves, pulsing with the rhythm of the nervous system itself. Muscles may twitch, limbs may feel weak or alien. The body reacts not just locally but systemically, as inflammatory pathways ignite. Swelling follows fast, and it is not superficial. Lymphatic vessels flood the area, immune cells pour in, and tissue pressure builds from the inside out. In some cases, the limb stiffens, movement restricted not by fear, but by physiology. Heat rises, skin tightens. Nearby lymph nodes may ache or enlarge as the body processes venom proteins and cellular debris. This reaction is not an accident. It is the immune system doing exactly what it evolved to do when confronted with a molecular intruder it does not recognize. What makes scolopendra bites particularly severe in human encounters is not just venom potency, but behavior under stress. Centipedes do not strike once and retreat. When threatened, especially when pinned or grabbed, they thrash. Their long bodies coil and twist, forcipules snapping repeatedly as legs search for purchase. Multiple bites can occur in seconds, clustered close together or spread along a limb. Each injection adds to the chemical load, amplifying pain, swelling, and systemic response. This is not aggression for dominance. It is survival logic, executed without hesitation. The forest sets the stage for these encounters quietly. Logs are lifted because they block paths. Stones are moved because they look dry. Hands reach before eyes because the ground is uneven and balance matters. At night, when temperatures drop just enough to make movement comfortable, centipedes become more active, hunting spiders, cockroaches, small lizards, even sleeping amphibians. A human hand entering this space is not seen as an enemy or prey. It is simply a sudden, massive disturbance that must be neutralized immediately. Sleeping on the ground compounds the risk. Body heat attracts invertebrates seeking warmth or moisture. A centipede exploring the edges of a sleeping mat or leaf pile may be crushed inadvertently, triggering a defensive strike inches from exposed skin. In these moments, there is no time to react, no chance to withdraw cleanly. The encounter is decided by proximity, not intent. From an ecological perspective, Scolopendra occupy a crucial niche. They regulate populations of other arthropods, keeping decomposer communities balanced. Their predation pressure shapes the behavior of spiders and insects, influencing where and when those animals forage. Even vertebrates respect them. Many small mammals avoid areas dense with large centipedes, not because of fear alone, but because the cost of a mistake is too high. In this way, venom becomes a structuring force in the ecosystem, invisible but effective. Thermoregulation plays a subtle role in this dynamic. As ectotherms, centipedes rely on environmental heat to fuel muscle contraction and venom delivery. Warm, humid conditions increase their responsiveness and strike speed. The same tropical nights that invite human movement, cooler, quieter, seemingly safer, also prime the centipede's physiology for action. Once again, timing favors the animal that has lived here longest. The camera lingers on a centipede retreating back into leaf litter, disappearing as seamlessly as it emerged. The disturbance is over. The forest resumes its layered noise. Nothing marks the encounter except the memory carried by the nervous system of whoever reached where they should not have. No warning rattle, no bright colors, just consequence delivered at close range. This is the lesson the leaf litter teaches without explanation. In this world, danger does not announce itself. It waits beneath what looks stable, beneath surfaces humans trust by habit. Under bark and stones, punishment replaces warning, and survival belongs to the organisms that strike first, not hardest. The forest floor looks settled at dawn, as if the night packed itself away neatly. Webs sag with dew between roots. Leaf litter steams softly as sunlight filters through gaps in the canopy. In this light, the tarantula appears almost ornamental, a dense, velvet-bodied spider crouched at the mouth of a burrow or pressed motionless against bark. Thick legs, slow movements, an animal that seems to embody restraint rather than threat. This is why the story so often goes wrong. People come here prepared for bites, for venom, for fangs. What they do not prepare for is contamination. The camera holds close not on the fangs, but on the abdomen. Thousands of fine hairs blanket it, catching light like dust on dark fabric. They look soft, harmless, even insulating. In reality, they are one of the most effective defensive systems an arthropod has ever evolved. Urticating hairs are not passive coverings. They are detachable projectiles, barbed, brittle, and designed to break free at the slightest provocation. When threatened, many New World tarantulas pivot their bodies and rake their hind legs across the abdomen, launching a cloud of microscopic darts into the air. There is no sound, no obvious strike, just a release. Each hair is a weapon scaled for biology rather than violence. Under magnification, they are jagged shafts tipped with backward-facing barbs, perfectly shaped to lodge into soft tissue. Skin, eyes, airways. They do not inject toxins. They do not pierce deeply. Instead, they embed themselves and refuse to leave. The immune system reacts instantly, recognizing them as foreign bodies it cannot dissolve. Inflammation follows. Histamines flood the area. Nerve endings fire persistently, not in sharp bursts, but in relentless irritation that does not resolve quickly. This is where the nightmare begins, not in the moment of contact, but in what follows. A hand brushes a hammock line where a spider passed hours earlier. Fingers adjust a boot left overnight. Someone wipes sweat from their face, unaware that the fine grit clinging to their skin is not soil, but hairs. The eyes come next, because eyes always come next. Rubbing is instinctive. It is also catastrophic. The motion drives the barbs deeper into the conjunctiva, scraping the cornea, turning a mild exposure into an injury that can last weeks. Inhaling urticating hairs adds another layer of misery. In dry conditions, disturbed leaf litter and old webs can release them into the air. Once inhaled, they settle along the mucous membranes of the nose, throat, and upper lungs. The result is a persistent burning sensation, coughing, tightness in the chest, symptoms that mimic infection or allergic reaction but do not respond quickly to treatment. The hairs remain physically present, provoking inflammation until they are slowly expelled or encapsulated by tissue. There is no antidote for this, only time and management. From the spider's perspective, this defense is elegant. Tarantulas are slow, they are large. They cannot outrun mammals or birds, and biting is a last resort that risks damage to fragile fangs essential for feeding. Venom exists primarily to subdue prey, not to deter predators. Urticating hairs solve that problem at a distance. A curious mammal that sniffs too close recoils in discomfort. A bird that attempts a peck targets the abdomen and receives a face full of irritant. The spider survives without escalating to physical combat. The evolutionary success of this strategy is evident in behavior. Tarantulas are not aggressive by default. They posture, they retreat, they warn. Only when those signals fail do they deploy hairs, and only after that do they consider biting. Humans misinterpret this sequence because they are focused on the wrong threat. They expect a puncture wound. What they get instead is a distributed, invisible exposure that spreads with their own movements. Campsites are perfect staging grounds for this mistake. Hammocks strung between trees intersect arboreal pathways. Wood piles attract insects, which attract spiders. Boots left open overnight become shelters. In the morning, routine reasserts itself. Gear is grabbed without inspection. Clothing is shaken once, maybe twice, and put on. A spider disturbed inside a boot may flick hairs reflexively before retreating, leaving the interior coated with microscopic barbs. Feet slide in. Socks trap the hairs against skin. Hours later, itching begins, spreading upward in patches that resist scratching and worsen with sweat. This is not danger in the cinematic sense. There is no dramatic attack, no sudden injury. It is slower, more insidious, and harder to explain to someone who has never experienced it. The irritation does not peak quickly and fade. It lingers, it migrates, it interferes with sleep, with vision, with breathing. In some cases, secondary infections follow as damaged skin becomes vulnerable to bacteria and fungi abundant in tropical environments. The original exposure may have lasted seconds. The consequences stretch far longer. Ecologically, tarantulas occupy a quiet but important role. They are long-lived ambush predators, consuming insects, small vertebrates, and scavenging opportunistically. Their burrows aerate soil. Their abandoned tunnels become shelters for frogs, lizards, and other invertebrates. They are not pests, they are infrastructure. Their defenses are calibrated not to kill indiscriminately, but to discourage interference. The fact that those defenses affect humans so effectively is incidental. not targeted. Thermoregulation intersects subtly with this story as well. During hot, dry periods, urticating hairs become lighter, more prone to dispersal. During humid nights, they cling to surfaces longer, increasing the chance of transfer through touch. Seasonal changes alter the risk profile without changing the animal's behavior at all. Once again, environment amplifies biology. The camera returns to the spider, now partially hidden beneath a log. It has not moved far. It has not chased or followed. Its defense was deployed and forgotten in the same motion. The forest does not reward excess. Efficiency is enough. Somewhere nearby, a human scratches an arm that will not stop itching, blinks eyes that feel full of sand, wonders why nothing visible explains the discomfort. This is the correction the tarantula offers to the venom narrative. The danger is not the bite. The bite is rare, controlled, and usually mild in systemic effect. The real hazard is what spreads without notice, what stays behind after the animal is gone. You did not get bitten, you got contaminated. The bark looks inert until the camera slows down. What seemed like a random patch of lichen resolves into symmetry. A line becomes a leg, a shadow sharpens into a head, angled just enough to break the illusion. Pressed flat against the trunk is a predator that has mastered stillness so completely it appears grown rather than arrived. An assassin bug waits, forelegs locked around a struggling insect pinned with surgical precision. There is no chase, no explosion of motion. The kill is already in progress before the prey understands it has been caught. This is camouflage taken to its logical extreme. Assassin bugs do not simply blend in, they erase themselves. Their bodies echo bark texture, leaf veins, fungal blotches, even bird droppings. Some species collect debris and glue it to their exoskeleton, building moving disguises that fool both prey and predators. In the layered visual noise of the Amazon, where every surface is patterned and nothing stays clean for long, this strategy is devastatingly effective. The forest is full of insects that rely on motion to identify danger. Against an animal that does not move, that logic fails. The camera tightens on the moment of feeding. The assassin bug's proboscis, a stiff, three-segmented rostrum folded beneath the head, swings forward and locks into place. This is not a piercing needle like a mosquito's, nor a chewing apparatus like a beetle's mandibles. It is a reinforced syringe, driven by muscle and intent. The tip finds a soft joint in the prey's exoskeleton and punches through. What follows is chemistry. Digestive saliva floods the wound, a complex mixture of enzymes designed to do two things at once: immobilize and dissolve. Proteases begin breaking down muscle tissue. Neuroactive compounds disrupt nerve signaling. Within seconds, the prey goes limp, not because it is dead, but because it has been turned into a container of liquefying nutrients. The assassin bug does not chew, it waits. Minutes later, it draws the partially digested contents back through the proboscis, leaving behind a hollow shell. This feeding strategy explains everything about what happens when humans get bitten, and why those bites are remembered with such clarity. When an assassin bug stabs human skin, it is not defending itself with a generic toxin. It is deploying a tool evolved to shut down living tissue fast. The pain is immediate and savage, often described as one of the sharpest insect bites known, not because of venom volume, but because of delivery. The proboscis penetrates deeply, anchoring itself, and the saliva begins digesting tissue that was never meant to be digested alive. The sensation is different from a sting. It is not spreading heat or throbbing ache. It is a focused, electric agony that seems to drill inward, as if something is actively working inside the wound. That impression is accurate. Enzymes are breaking cell membranes apart. Local inflammation spikes instantly as the immune system recognizes catastrophic tissue damage. Blood vessels dilate, nerves fire continuously. Even after the bug disengages, the chemistry remains, continuing its work. What makes encounters with assassin bugs especially common is not aggression, but misidentification. Many species resemble harmless plant bugs, leaf-footed bugs, or even beetles at a glance. They move slowly. They do not buzz. They do not announce themselves. A hand reaches out to brush one away from clothing. Fingers close reflexively. The bug responds with the only tool it has. In camps and forest edges, where people handle firewood, sort gear, or flick insects aside without looking closely, this mistake repeats itself endlessly. Clothing is another vector. Assassin bugs rest in folds of fabric hung overnight, attracted by warmth, moisture, or the insects drawn to sweat residue. When disturbed suddenly, a sleeve pulled on, a shirt shaken, they strike at the nearest contact point. The bite often lands on thin skin, wrists, neck, upper arms, places rich in nerves and blood supply. The initial pain is so sharp it overrides context. People drop what they are holding, shout, panic. By the time they see the insect fall away, the damage is already done. Then comes the second phase, the one that lingers. Pain does not simply fade after the bite. It intensifies in waves as inflammation builds. Swelling spreads outward from the puncture site, sometimes disproportionate to the size of the wound. The area becomes hot, firm, exquisitely sensitive to touch. Hours later, secondary irritation sets in, itching layered over pain, a sign of histamine release and immune activity. In tropical environments, where skin is rarely dry and bacteria are everywhere, the risk of secondary infection increases, especially if the bite is scratched or broken. This delayed misery is part of the assassin bug's effectiveness as a predator and, unintentionally, as a hazard to humans. The saliva is optimized not for instant kill, but for efficient external digestion. It keeps working until it is neutralized or cleared. Unlike venom injected by stinging insects, which is often metabolized quickly, these enzymes persist, continuing to irritate tissue long after the encounter ends. Treatment focuses on symptom control, cleaning, cold, anti-inflammatories, because there is no antidote to enzymes already at work. From an ecological standpoint, assassin bugs are essential regulators. They prey on a wide range of insects, including agricultural pests and disease vectors. Their presence shapes insect communities, reducing outbreaks that could strip vegetation or spread pathogens. Some species specialize, others are generalists, but all rely on the same core strategy: precision over power. They do not overpower prey with strength, they dismantle it chemically. Thermoregulation intersects subtly with their activity patterns. Assassin bugs are most active in warm conditions that keep their enzymes fluid and effective. Cooler temperatures slow digestion and feeding, so they retreat into sheltered microhabitats, bark crevices, leaf axils, fabric folds. These are exactly the places humans interact with most during rest and setup, not during movement. The overlap is not coincidental. It is ecological geometry. The camera returns to the original predator on the bark. The prey is now motionless, hollowed out, its role in the ecosystem concluded. The assassin bug cleans its proboscis meticulously, wiping it against the substrate, careful not to foul its own body with the same chemicals it uses to kill. It does not linger. It does not posture. The forest does not reward drama. Somewhere else, a human examines a swelling bite that does not make sense for its size, replaying the moment of contact again and again, wondering how something so small could hurt this much. That question misses the point. In the Amazon, effectiveness is not measured in muscle or mass. It is measured in chemistry, delivered with precision. The weapon was never strength. It was always the saliva. At first, it looks like a trick of light. The forest floor seems to ripple, as if heat is bending the air just above the leaf litter. Then the movement sharpens. The ripples gain edges. What appeared to be shadow becomes structure, and structure becomes motion with intent. A dark band flows between roots, pours over fallen branches, splits around stones, and rejoins without slowing. The ground itself is moving, not in patches, not in bursts, but as a continuous living wave. This is an army ant column at full momentum, and once you see it clearly, you understand that standing still is already a mistake. Army ants do not hunt as individuals. They do not stalk, ambush, or retreat. They advance. Their power lies not in venom, speed, or size, but in coordination so tight that it functions like a single organism spread across thousands of bodies. Each ant follows chemical trails laid seconds earlier by the ones ahead, adjusting direction, speed, and density in real time. There is no central command issuing orders. Intelligence emerges from contact, antennae brushing, pheromones refreshed, paths reinforced by use. What looks chaotic up close resolves into disciplined flow when viewed from above. The camera drops low, level with the leaf litter, and the scale becomes apparent. The column is not a line, but a braided river of bodies, workers streaming outward, soldiers flanking the edges, mandibles open and probing. Anything small enough to be overwhelmed is already doomed. Spiders, beetles, centipedes, even small vertebrates freeze too long and vanish under the swarm, disassembled piece by ants that never pause to eat. Food is processed later. The hunt does not stop for digestion. This strategy eliminates the need for venom. Army ants do not need to incapacitate prey chemically when they can simply apply force everywhere at once. Each bite is small, sharp, and local. One bite means nothing. 100 means pain. 1,000 means panic. The agony is cumulative, stacking faster than the nervous system can adapt. Pain receptors fire continuously, overlapping signals blurring into a single urgent message. Move now. For humans, the danger is not a single injury, but the speed at which control evaporates. The first ants climb shoes and socks unnoticed. Their bites register as pinpricks, easily ignored. Then ankles begin to burn, calves itch sharply. Hands slap instinctively, brushing ants higher up the body, spreading the problem rather than solving it. The column does not break. It flows around obstacles, including people, and any pause increases exposure exponentially. What makes this especially dangerous is how quickly panic feeds back into the situation. Pain drives movement. Movement shakes clothing loose, opens gaps, dislodges ants onto skin that was protected seconds earlier. People stumble on roots they would normally step over easily. Falls happen. Once on the ground, the swarm finds everything: neck, ears, scalp, groin. Soft tissue targeted not intentionally, but inevitably. The ants do not aim. They simply occupy space, and space includes you. The forest has evolved alongside this force, and most animals know how to respond. Birds lift off before contact. Mammals bolt early. Even snakes abandon kills rather than face a column. The few species that exploit army ants do so from above or behind, picking off flushed prey without touching the swarm itself. Nothing tries to fight it head-on. Humans, unfamiliar with this logic, often hesitate too long, trying to understand what they are seeing instead of reacting to what it means. Understanding the swarm's logic reframes the encounter. Army ants do not chase individuals. They advance along a route optimized for prey density and terrain efficiency. Columns can be meters wide and hundreds of meters long, shifting direction as food availability changes. When a human intersects that route, the ants do not divert. They cannot. Their coordination depends on momentum. Stopping to pick ants off disrupts balance without reducing exposure. The only effective response is decisive movement away from the flow, crossing it at speed or retreating along a clear path. Survival cues are simple but counterintuitive. Do not stand still. Do not kneel. Do not try to brush ants away one by one. Move out of the column's path as quickly as footing allows, ideally perpendicular to its direction of travel. Once clear, remove clothing immediately if possible, shaking ants off before they find shelter in seams and folds. Delay turns dozens of bites into hundreds. Hesitation compounds pain. What not to do matters just as much. Do not run blindly. Falls increase surface contact dramatically. Do not scream and flail, which wastes energy and spreads ants upward. Do not sit down to deal with it. The swarm does not respect personal space. It fills it. Calm is not comfort here, but it is function. The goal is not to endure pain, but to shorten exposure time. From an ecological perspective, army ants are architects of disturbance. Their raids reset insect communities, flush hidden animals into the open, and redistribute nutrients across the forest floor. Areas recently swept by a column look stripped, but recovery is rapid. Plants benefit from reduced herbivory. Scavengers exploit leftovers. Even soil structure changes as ants excavate and rebuild temporary nests. The forest pulses around their movement, a rhythm as fundamental as rainfall. Thermoregulation plays a role in when and how these swarms move. Army ants are most active when temperatures allow sustained metabolic output without overheating. Too hot, and the column fragments. Too cool, and coordination slows. Their timing often coincides with human activity, early morning, late afternoon, when trails are used and camps are active. Once again, overlap is not malicious, it is mathematical. The camera pulls back to show the column from above, a dark vein threading through green. It does not stop for anything. It does not acknowledge obstacles. It advances, consuming opportunity as it goes. Minutes later, the forest behind it looks calmer, emptier, deceptively peaceful. Nothing marks the passage except the absence of what was there before. For the human caught in that wave, the memory is not of individual bites, but of losing control, of limbs not responding cleanly, of decisions collapsing under sensory overload. That is the real curse of army ants, not venom, not injury. But the moment when pain hijacks judgment, and the forest reminds you that coordination beats strength every time. At first glance, the trail edge looks busy but benign. A steady stream of green fragments moves along a narrow path cut into the soil, each piece of leaf carried upright like a banner. Leaf cutter ants are among the most photographed insects in the tropics for a reason. Their procession reads as industry rather than danger, agriculture rather than aggression. They look organized, purposeful, even charming, a living illustration of cooperation. That is the mistake. What you are watching is not a parade, it is a factory line built on blades. The camera drops closer, low enough to hear the faint rasping sound beneath the forest noise. It is subtle, almost lost beneath birds and insects, but it is there. A dry, repetitive scraping as mandibles meet plant tissue. Leafcutter ants do not tear leaves, they cut them. Each worker braces itself, anchors with hooked feet, and swings its head in a precise arc, closing mandibles that are harder than steel at this scale. Zinc and manganese reinforce the cutting edges, giving them durability and sharpness unmatched among insects. Evolution has turned jaws into tools so efficient that engineers study them for inspiration. This same machinery that turns foliage into farming substrate does not change when it meets skin. A leafcutter bite is not venomous. There is no burning toxin, no chemical hijacking of nerves. Instead, there is pressure, alignment, and a closing force that behaves like a punch biopsy. The mandibles shear cleanly through the outer layers of skin, often without immediate pain because the cut is so sharp and so fast that nerve endings lag behind. Blood appears first. Pain follows a heartbeat later, sharp and localized, as if sliced by a fresh razor. One bite is manageable. That is never the problem. Leafcutters operate in dense traffic zones. Trails run like arteries between nest entrances and cutting sites, sometimes buried, sometimes exposed, often crossing the exact places humans choose to kneel, sit, or steady themselves. A knee touches down on what looks like quiet ground. Fingers wrap around a vine used by hundreds of ants as a highway. The response is instantaneous, not coordinated by alarm, but triggered by contact. Ants do not flee, they clamp. Multiple workers bite at once, each cut shallow but clean, each jaw closing with mechanical certainty. In seconds, dozens of incisions open across skin, bleeding freely because nothing cauterizes or constricts the wounds. The result is disproportionate to the size of the animal. A spatter of blood, thin rivulets running along limbs, spots blooming through fabric. The pain escalates not through depth, but through number. Tiny injuries stack faster than the brain can catalog them. Unlike army ants, leafcutters do not swarm aggressively up the body. They hold position. They bite and stay attached, jaws locked, requiring force or leverage to remove. Pulling them off often worsens the damage, tearing tissue rather than releasing it cleanly. Panic sets in not from overwhelming pain, but from the sudden realization that something small is cutting you faster than you can react. From the ant's perspective, this behavior makes sense. Leafcutters are not predators. They are farmers defending infrastructure. Their trails are lifelines connecting fungus gardens, vast underground chambers where leaf fragments are cultivated into food. Any disturbance threatens the colony's survival. Mandibles evolved to process vegetation, double as defensive tools, and there is no reason for the ant to modulate force when contact is made. Skin is just another material in the way. The aftermath is where the real danger lies, and it is quieter than the encounter itself. The wounds look superficial, they often are. But the Amazon is not a clean place, and these cuts are made at ground level, where bacteria, fungi, and parasites thrive. Soil particles, plant debris, ant secretions, all are driven into open skin. In the humid heat, wounds stay moist, slowing clot formation and prolonging exposure to microbes. Healing becomes a negotiation rather than a process. Cuts scab poorly, redness spreads. Itching joins pain, tempting scratching that reopens wounds. In some cases, infections take hold, turning clean slices into inflamed lesions that persist for weeks. What should have been trivial injuries become persistent problems, not because of the ant's intent, but because of the environment's indifference. This is compounded by human behavior. People underestimate leafcutter bites precisely because they lack venom. There is a tendency to ignore them, to rinse briefly and move on. In temperate climates, that might work. In the jungle, it does not. Constant moisture macerates skin. Sweat feeds microbes. Movement reopens cuts. The forest does not forgive neglect. Ecologically, leafcutter ants are foundational species. Their agriculture reshapes landscapes, influences plant composition, and aerates soil on a massive scale. A single mature colony can move tons of vegetation annually, redistributing nutrients and altering light patterns as favored plants are repeatedly harvested. Their fungus gardens are monocultures requiring constant input and defense, and every worker is specialized to maintain that balance. This specialization explains the precision of their bite. Mandibles are tuned not just for cutting, but for consistency. A leaf fragment too thick or too thin compromises fungal growth. The ant's nervous system is calibrated to deliver the same motion thousands of times a day without error. When that motion is applied to skin, the result is not random injury. It is standardized damage, repeated rapidly. Thermoregulation influences when and how these encounters occur. Leafcutters avoid the hottest parts of the day to prevent overheating while carrying loads. Their peak activity often coincides with times humans rest. Midday breaks, evening camps, moments when vigilance drops. Trails that seemed inactive hours earlier suddenly fill with movement as temperatures shift. Sitting down without scanning becomes an invitation. The camera follows a worker ant returning to the nest, leaf fragment held high, passing beneath a boot that narrowly misses the trail. The scale difference is absurd, yet the risk flows upward, not down. The colony continues its work uninterrupted, oblivious to the blood left behind by an animal that never learned to look before kneeling. As the scene closes, the focus returns to the wounds. Thin, straight cuts, already crusting at the edges, deceptively neat. They do not look dangerous. That is the final trick. The pain was clean, the blades were perfect. But what follows is slow, messy, and shaped by everything the jungle holds in reserve. The edge of the Amazon is not a clean line between forest and safety. It is porous. It leaks, roof lines blur into canopy, walls crack and breathe, gaps open where heat escapes and insects gather. At dusk, when the air cools just enough to move, those gaps become gateways. Bats begin to flow through them, tracing flyways so consistent they look choreographed, slipping out from under eaves, from palm thatch seams, from hollow beams where daylight never quite reaches. This is not wilderness pressing in. This is wildlife already inside. From the outside, it looks peaceful. Dark silhouettes flicker against a fading sky, wings slicing silently through air thick with insects. Bats are masters of efficiency here. Their echolocation paints three-dimensional maps in darkness, letting them skim millimeters from walls without contact, scoop prey mid-flight, and return to roosts with precision that feels almost surgical. For most people living at the forest's edge, this nightly emergence fades into background noise, as familiar as frogs or rain. That familiarity is what makes the danger invisible. The camera follows a bat back inside, through a narrow roof gap, into a space that smells of dust, guano, and old wood. The temperature is stable, protected from daytime heat and nighttime chill. Bodies cluster together, conserving energy, sharing warmth. This is where risk begins, not in dramatic attacks, but in proximity. Bats do not need to seek humans out. Humans build shelters that mimic caves, and bats accept the invitation. The bite, when it happens, is often forgettable. Some bat species feed on insects only, others on fruit or nectar, but a few feed on blood, and many more will bite defensively if handled, trapped, or disturbed. Their teeth are small, sharp, and optimized to pierce skin cleanly. A defensive nip or feeding cut can feel like nothing more than a pinprick, especially if it happens during sleep. There is rarely tearing, rarely bleeding enough to alarm. The wound closes quickly, leaving little evidence that anything happened at all. That is the problem. The real danger is not the mechanical injury. It is what crosses the barrier. Saliva enters tissue. Viruses move with it, invisible, indifferent to how small the opening was. Rabies is the name that matters most here, not because it is common in every bat, but because when it does transmit, it rewrites the rules of survival. The virus travels along peripheral nerves, moving slowly, deliberately, toward the central nervous system. There is no pain to mark its progress, no fever at first, no dramatic warning. The decision point arrives early and passes quietly. A scratch noticed in the morning, a tiny scab on a finger. A bat seen in the room overnight that flew out before anyone thought much of it. The logic kicks in immediately. It's nothing. It didn't hurt. There's no blood. I would know if something was wrong. In the Amazon, this logic is deadly, not because it is foolish, but because it is human. Rabies exploits hesitation. Once symptoms appear, anxiety, confusion, tingling at the bite site, difficulty swallowing, the outcome is almost always fatal. Treatment works only before the virus reaches the brain. After that threshold, medicine is reduced to comfort care. The virus does not rush, it waits. It gives people time to dismiss it. This is why bats occupy such a strange position in the ecology of fear. They are not aggressive, they are not hunting humans. They are essential pollinators, seed dispersers, insect controllers. Entire forest systems depend on their nightly labor. Fruit bats regenerate clearings. Insectivorous bats keep mosquito populations in check. Remove them, and disease risk skyrockets from other vectors. The animal itself is not the villain. The interaction is. Thermoregulation explains part of the overlap. Bats seek stable temperatures to conserve energy. Human houses provide that. During cooler nights or heavy rain, bats may move deeper into structures, increasing the chance of contact. Young bats learning to fly crash land more often, ending up on floors or tangled in clothing. People pick them up, trying to help, unaware that gloves and distance matter more than good intentions. The nervous system becomes the true battlefield. Rabies does not destroy tissue directly. It hijacks neurons, using them as highways. It alters behavior before it shuts the body down. Fear, agitation, hallucinations, symptoms that once inspired myths and curses now have a biological explanation that is more unsettling than superstition. The virus turns the body against itself, weaponizing its own wiring. The camera lingers on a quiet bedroom at dawn. Light slips through cracks in the wall. A mosquito net hangs loosely. There is no sign of intrusion, no blood on sheets, no damage. Somewhere above the ceiling, bats settle back into roosts, their night complete. The human below wakes up, stretches, notices nothing unusual, and moves on with the day. This is the curse theme at its most refined. Not pain, not violence, not spectacle. A microscopic exchange at the edge of awareness that carries consequences wildly disproportionate to its size. The smallest wound becomes the biggest problem because it bypasses muscle, skin, and instinct, heading straight for the system that makes decisions in the first place. The Amazon does not always attack through teeth or claws. Sometimes it enters through silence, through trust, through the assumption that danger must hurt to matter. Sometimes it attacks through the nervous system, long after the bat has gone back to sleep. The story usually begins with relief, a splash in the shallows, a sudden weight, a flash of armored motion just beneath the surface, and then release. The person stumbles backward, heart hammering, water churning where a caiman surfaced and vanished. There is blood, yes, but not much. Teeth marks, shallow punctures, maybe a crushed finger or torn boot. Compared to the stories everyone knows, death rolls, dragged bodies, disappearances, this feels like luck. A small bite, a warning, survival. That feeling does not last. In the Amazon, a caiman encounter rarely ends when the jaws open. It only pauses. What looks minor in the first minutes often becomes catastrophic over the next days, not because the animal returns, but because the water does its work. The danger shifts from muscle and bone to biology, and the fight moves from riverbank to bloodstream. Caimans are not built to slice cleanly. Their teeth are conical, blunt, designed to grip and crush rather than cut. Even a brief bite delivers enormous pressure, compressing tissue far beyond what skin damage alone suggests. Beneath small puncture wounds, muscles are bruised, blood vessels ruptured, and microscopic fractures form in bone. The injury hides its depth. Pain may be muted at first, overridden by adrenaline, by shock, by the overwhelming relief of escape. Then there is the water. Amazonian rivers are not sterile environments. They are living soups of bacteria, fungi, protozoa, and parasites, enriched by organic matter and warmed year-round to temperatures ideal for microbial growth. A caiman's mouth adds another layer. Like all crocodilians, caimans carry dense bacterial communities in their oral cavities. Organisms adapted to survive on rotting prey, stagnant water, and biofilm, coated teeth. When those teeth enter flesh, they do not just puncture, they inoculate. The camera lingers on the wound hours later. Swelling has increased, skin is tight, shiny, warm. What were pinpricks now ooze cloudy fluid mixed with blood. This is not simply inflammation from trauma, it is infection gaining momentum. Bacteria introduced deep into crushed tissue find an environment low in oxygen, rich in damaged cells, perfect conditions for explosive growth. Antibiotics, if available, must fight uphill from the start. This is where the spiral begins. Pain increases instead of fading. Redness spreads along lymphatic pathways. Fever creeps in, subtle at first, then undeniable. Muscles stiffen not from injury alone, but from the body's systemic response to invasion. In severe cases, necrosis sets in. Tissue starves as swelling cuts off blood supply, turning viable muscle into dead matter that must be removed surgically or left to rot. Surviving the bite was never the real victory. It was step one. Human behavior makes this worse, not through recklessness, but through necessity. Fishing happens at the water's edge because that is where fish are. Nets must be retrieved, lines must be untangled. At night, visibility collapses, reflections hide movement. The caiman's eye shine appears only when light hits at the right angle, and by then distance is already gone. Wading to knee depth feels manageable. It often is, until it isn't. Caimans do not hunt people deliberately, but they defend space and investigate disturbances. A hand splashing while pulling a net mimics prey. A fish struggling on a line draws attention. In these moments, bites are often exploratory or defensive, not full predatory strikes. The animal clamps, tests, releases. That release saves a life and endangers it at the same time. What follows depends less on the caiman and more on what happens next. Clean water is rare, soap is rarer. Many people rinse wounds in the same river that caused the problem, unknowingly reintroducing contaminants. Dressings stay damp in humidity that never drops. Travel to medical care can take days, sometimes longer than the bacteria need to establish dominance. The ecological context matters here. Caimans are apex regulators of aquatic systems. They control fish populations, scavenge carrion, shape riverbank behavior of other animals. Their presence signals a functioning ecosystem. The same rivers that sustain human communities depend on them. This overlap is not optional, it is structural. People fish where caimans live because that is where food is. Thermoregulation adds another layer of risk. Caimans bask during the day and become more active at night when water temperatures equalize and prey movement increases. Humans, seeking relief from heat, also favor evenings and early mornings. The overlap peaks exactly when visibility drops and reaction time matters most. Biology and routine collide. The camera follows a survivor days later. The initial relief has evaporated. Walking hurts. The wound smells wrong. Sleep is broken by fever dreams. What was dismissed as a small bite now dominates every decision. Work stops. Travel becomes urgent. In some cases, limbs are lost not to the jaws, but to the aftermath. Infections that outrun treatment, tissues that cannot be saved. There is a quiet irony here, earned rather than forced. The caiman did not need to kill to win. The river finished the job it started. This is not a failure of courage or toughness. It is a reminder that survival in the Amazon is measured on timelines longer than the moment of impact. The camera returns to the river at dusk. The surface smooths. Insects skim. Somewhere below, a caiman glides through tannin dark water, indifferent, ancient, doing what it has always done. The encounter is over for it. For the human, it is just beginning. In the Amazon, you can win the moment and still lose the week.